So all of you should send your name in the chat box. Can you see the screen? Are you able to see the screen?
Yes, ma'am.
Somebody has to answer.
Yes, ma'am.
All right. So I was telling you in the last class that you have basically a gamma, a source is there. Source is whatever we have in the laboratory. And then gamma emits in all directions. If you keep a detector here, let us say, it's only receiving radiation in that particular direction. So this detector, job of this detector is to count the gamma rays depending on its energy. So you will determine the energy of the gamma ray. That's what you do in your experiment. I want to tell you, any gamma ray is characterized by its L value, multipole value, and associated M value, and its energy. These are typical and either electric type or magnetic type. Can I determine? These are theoretical nomenclatures that I have got for electric and magnetic fields. Can I identify these things when I detect a gamma ray? That is what is the aim of this particular session, which continues in next session also. So let me tell you, what do I mean by angular distribution? That is, at one particular direction, you find some set of gamma rays. Why not it go in some other direction? It does go, but how does it distribute itself? What is the distribution of gamma rays? So let me say first, distribution means angular distribution of energy in the multipole radiation is characterized by the Poynting vector. This is what I am saying. It's very, very heavy sentence. Let me explain it to you. So what I am saying here is, if you have energy, you are detecting energy. But I want energy in a particular direction, angular distribution of energy. Energy in a particular direction is what I want, and that too for a multipole radiation. That is, gamma is known to have all these L, M, and E gamma, all that is there. My intention is to find, if I find a gamma ray at an angle, let us say theta phi, what is its energy at that particular angle theta phi? And similarly, I want to know counts, number of counts in the direction theta phi. How do I do it is the question. You know that energy of any electromagnetic radiation is given by, energy radiated is given by what is called as a Poynting vector, and it is given by E cross B. It is proportional to electric field cross product with magnetic field. Energy is given in terms of this vector, modulus of that gives you energy, is what you have learned in your electrodynamics. So I am saying energy, angular distribution of energy can be determined. It's characterized by the Poynting vector. I write Poynting vector as my notation is S, and that is given by some mu naught into E cross B, which is energy per area into time. That is energy per unit area per unit time. If you keep checking what is the radiation coming, what is the energy of the radiation per unit area, per unit time, that's what is given by this Poynting vector. Generally, I am interested in multipole radiation where E contains a L value, B contains a L value, etc., etc. Now, we focus on the so-called wave zone. Why we restrict to certain zones? It is only because I cannot simplify the expression otherwise. So I restrict to a physically motivated wave zone, which means that it's a region very, very far away from the source. In the wave zone, we will write K into R is much, much larger than 1. That's what corresponds to far away region. K is corresponds to energy. R is where I am looking at, distance at which point I am looking at. If K into R is much larger than 1, we call it the wave zone. So if we use that particular approximation, in that case, I can show, because what is electric field, magnetic field, we know what is the structure of electric and magnetic fields. So I will just indicate it to you. That is what you have is, suppose I take a B, E, L, M of R. What is this equal to? This you know, I will write proportional because I may miss the numbers there and all that. So this is going to be given by some spherical Hankel function combinations and a L acting on YLM of theta phi. It is proportional to this. Then if I take K into R much, much larger than 1, I know certain properties of spherical Hankel functions. There are two types. So if I say HL of 1 of R, in the wave zone, KR much greater than 1, I know its form, functional form, very, very easy to write. Otherwise also I know the form, but I can simplify it in the limit KR very larger than 1. So I am only saying it. If you are curious, you can check spherical Hankel functions. I will write what is the BELM of R in the limit KR much larger than 1. In that case, this is going to be minus 1 minute. Just a minute. So, what am I saying? So, I am using what is called as wave zone. And in the wave zone, I can simplify what is the multipole field, magnetic field of the electric type. This takes a form e to the IKR, pi KR, LYLM of theta phi. Or in other words, what I am saying is, in this limit, my FL of KR, in the limit KR much, much larger than 1, it takes the form e to the IKR divided by, say, KR. So that is easier to simplify than a very complicated spherical Hankel function. So I use that and write what is the spherical Hankel function reduction in the K into R much larger than 1. If you want to know what is that KR much larger than 1, how does it mean far away from the source? I will only tell you, take this K into R much larger than 1. So do you know what is K? K into C into K is omega, right? Omega is C into K. So R, I will say omega is 2 pi by lambda. So R, I will say that K, okay, if I multiply this with, just a minute, C into K is this, or lambda is equal to 2 pi divided by C into K. So instead of K, I will substitute, instead of K, wherever K is there, I will write 2 pi divided by C into lambda. If I am substituting it right, then I will get R, K is 2 pi divided by C into lambda, that is much larger than 1, which also means that R is much larger than lambda. That is, lambda corresponds to a region where I am looking at whatever is the source region. If that is, R is much larger than lambda, means I have a far away region where wavelength is smaller compared to R. So that is why I am taking such a limit. This is not required for your exam, but there is a meaning in all these wave zone, near zone, all that, where the spherical Hankel functions or whichever functions appear in the solutions, they have a reduction. They show you some simpler structure. So once I do that, I write, substitute L is equal to minus I R cross del and write for the corresponding electric field, what is that I get? Electric field in that wave zone, it is going to be minus I power L divided by K squared and gradient of e to the I K R by R crossed with L by Lm. That is, I simplify it. There are two terms, del operator acting on only e to the I K R by R, and the other term is e to the I K R by R is taken out, curl of R. So if you recall, what is the electric field expression in your multipole expansion? You write B E L M of R, that is FL of KR proportional to FL of KR L YLM of theta phi. That is, I am writing without any too many things. That is not coefficients here. So this is LM, electric field, magnetic field is what you know. Similarly, you write EELM of R, that is proportional to curl of B. That's from Maxwell's equations. So now what you are saying here, you are taking curl and BELM, in that FL of KR takes the form e to the IKR by KR when in the wave zone. So I will take e to the IKR by KR and I should write L acting on YLM of theta. So we have to write this, and then this has two terms, curl of, del gradient acting on e to the power IKR by KR. Do this first and then take a cross product of L YLM of theta phi. I have to always remember what is a vector and what is not a vector, etc. This curl then acts on, I take out e to the IKR by KR, curl of L YLM of theta phi. There are two terms. I'm just writing it, not going to simplify, and you need not worry about what will I get, etc. I'm showing to you that it is easy to do these things. One can try to do if you know, if you are familiar with the mathematics. Once I get that, I will continue. I ignore higher powers in 1 over R and simplify. That is, I don't consider powers of 1 over R because R is much, much, much larger compared to the source dimension. K into R is very, very larger. If you have a denominator which is, say, 1 over infinity, it goes to 0. So this is 0. So if 1 over KR, where KR is much, much larger than 1, I can take 1 over KR whole squared, and terms are there. So then I will say higher terms can be ignored. You take only up to the order 1 over KR, like that. So I will ignore higher powers in 1 over K into R. I am saying 1 over R. Then simplify. Then I get EELM of R is nothing but, it can be written as BELM crossed with unit vector R hat. I'm not showing you how I got this. I'm only telling you, if you take a simplification of this term, you can express it as BELM crossed with direction, unit vector in the direction of R. So let me again explain what is this mathematics. What does that mean? I will tell you that there is a BELM. Fine. That has a form, structure is there. In the KR very, very larger than 1. So similarly, I write what is EELM of R. That is, I'm showing that this goes to BELM. It is related to magnetic field crossed with unit vector R hat is what I am telling you. That is, if you take this kind of a thing, my intention is to find what is the Poynting's vector corresponding to a given multipole value. I want to know what is the angular distribution of energy. So I am taking what is electric field, what is magnetic field in the known region, that is in the wave zone is what I am checking, because I'm looking at detecting the gamma ray in the wave zone. So once I write this, I say where this is fine. So we know first, I want to tell you the properties of this electric and magnetic fields. I will tell you that if you take EELM is given by BELM crossed with R. Fine. So now take what is BELM of R. Take a dot product with EELM. I am just asking you to do that. Can you do that? What is EELM? I have written it here. Can you tell me what is B dot E in this form? Please know that I'm trying to get connected with you because you get lost in the notations. I'm talking about electric and magnetic fields in the wave zone. I can simplify mathematics and I'm asking you, I obtained and that electric field in the wave zone is B cross R. That's what I told you. Now I am asking you a question. You know vector algebra. Take a dot product of B with the E, where E is given by this expression. Can you tell me what is that? Do you know dot product? E is given in terms of B cross R. Can you tell me what is the dot product of BELM? Don't substitute anything for BELM. Only substitute what is EELM and tell me what is the dot product. Do you know what is the dot product of, let us say, A dot, A cross, say, R hat? Do you know this? Do you know vector algebra? What is the direction of A cross B? Direction.
Is it 0?
What is the direction of A cross B? Is it in the direction of A? Is it in the direction of B? Or is it perpendicular to A and B?
Perpendicular.
So then what is A dot A cross B?
0.
So I am asking you same question here. What is it? A
0.
dot A cross R.
It's 0.
So you should know notation change doesn't mean anything. So now tell me what is B dot E. What is E? I have written it here. I am asking you to substitute for E as B cross R. All this alankara, ELM and all that, forget it. It's a vector. E is B cross R. So there is a B dot B cross R. What is the value of B dot B cross R? What is it?
0.
0. Louder. So what I am telling you is this, if you know, in the wave zone, E and B are perpendicular to each other. One thing, one property that I have obtained is in the wave zone, I have written what is E vector. E vector is B cross R. So that tells me that E and B are perpendicular to each other. And also, I want to know what is the magnitude of E and B. So I want to tell you a very, very important concept that electromagnetic field has. So I am telling you that there is a BELM of R. Keep it. And EELM of R in the wave zone, it is approximately given by BELM of R crossed with R hat. That's what tensor cross product with R hat. Now I want to know what is the magnitude of EELM of R. I want the magnitude. If I give you A cross B, a vector is there, magnitude. I want to know what is the magnitude of A cross B. What do you tell me? Do you know magnitude of A cross B? Suppose I tell you A and B make an angle. Angle between A and B is theta. Now, will you tell me what is A cross B?
Magnitude of A into magnitude of B and sine of
Sine
theta.
theta. Sine theta. Cos theta is dot product. Sine theta is cross product. Right? Is that agreed? Agreed or no?
Yes, ma'am.
Now tell me what is EELM magnitude. It's a cross product. So I have to write what? Magnitude of B, LM of R. Write a magnitude of that. And then what? I want you to tell me. I have written only part of this multiplied by
Sine of theta between B and R.
R. Okay. So do you know what is the angle between R dot BELM of R? Electric type magnetic field is transverse magnetic. You remember that? Electric type is 0. So R dot B is 0. What does that mean? Theta is
90 degrees.
Theta is 90 degrees. Angle cross R is perpendicular to B. So theta is 90 degrees. So now tell me, BELM I have written. And what should I write here then?
1.
1. Because magnitude of R hat is 1 and sine 90 degree. I have to write sine 90 is 1. So magnitude of electric field is equal to magnitude of electric field. So that is what I am saying here without showing all those things. Now what I am saying is EELM and BELM are perpendicular to each other because EELM dotted with BELM is 0. So I have perpendicular. And another thing that I am talking, two things that I am talking. One is E dot B is 0 and also they have same magnitude. EELM magnitude is equal to BELM. Now, do you recall what is an electromagnetic field? That is, if I am telling you a electromagnetic radiation. How is it characterized? By its electric and magnetic fields. We say if there is a radiation, magnitude of E is equal to magnitude of B and E dot B is equal to 0. Do you remember this? This is property of a radiation. I'm telling you, you are getting it in the wave zone. That is, you have in the wave zone where you find a electric and electromagnetic radiation. This is what you are explicitly seeing in my calculation. So this is known to you. Any radiation should satisfy this property, correct? Do you know this concept? Electromagnetic radiation or electromagnetic field is nothing but there is electric and magnetic field vectors have same magnitude and E dot B is 0. This is something that you have learned at least I think in B.Sc also. Have you learned it in B.Sc or in M.Sc? Have you heard about this? Not learned. Heard? Not heard. You don't know it or do you know it? I'm asking. Yes or no is enough for me. Because I want answers.
We do. We know, ma'am.
Okay, fine. Good. So I am showing you your whatever you have got as a multipole radiation here. This is electric field and magnetic field are perpendicular to each other. And also they have same magnitude is what I am showing you. Thus, the magnitude of the pointing vector is given by, because my intention is always to find what is the pointing vector. I want to know what is the magnitude of pointing vector because that is the energy per unit area per unit time. That's what is the meaning of pointing vector. What is pointing vector? It is E cross B. So magnitude of S is EB sine 90 because electric and magnetic fields are at 90 degrees. So I will write this as, because S is defined here, where is it? It's mu naught into E cross B. I have to substitute everything. Then I do find that it is going to be given by C divided by 4 pi. How does it come? Don't ask me. It is, I have to take care of all proper units there. So if you know what is mu naught is basically C divided by 4 pi, if you check it. So I do write C by 4 pi and B mod squared. That's what is the Poynting's vector magnitude. So which tells me that I know what is magnetic field. Magnetic field is given by this. This is known to me. I have reduced everything to B mod squared. So I repeat again. So my intention in doing the angular distribution is I want to find magnitude of Poynting's vector. And Poynting's vector is given by mu naught into E cross B. This is what is given. What I have shown you is your B electric type magnet vector in this. This is, I give you expression E to the IKR by KR L acting on YLM of theta phi. If you sit with it, you can simplify it, whatever it is. But I know this. Then I showed you that your electric field vector, in the wave zone, it is of the form BELM crossed with R unit vector. So this tells me that E and B are perpendicular to each other, and E is magnitude wise, it is same. With all these identifications, I come back to Poynting's vector and tell you that Poynting's vector mu naught E cross B is E into B, that is B mod squared. That's all I have. This mu naught, I can simplify it as C divided by 4 pi. Go and check what is mu naught. It can be written as C divided by 4 pi. So I get, in terms of a known magnetic field, expression for magnetic field is known to me. I write what is the Poynting's vector. Do I have to use it for my further calculation? Yes, I need to use it. So what I'm telling you is, again emphasizing, S gives the electromagnetic energy escaping per unit area per second. Don't get lost with the word escaping. I have a charge distribution. There is electromagnetic energy coming out of the source there, and that is given by magnitude of S. That gives you energy per unit area per unit second. Now, to obtain energy emitted into a solid angle element, d omega sin theta d theta d phi. Okay. Now let me again repeat. These are not very complicated concepts. Concepts wise, what I am telling you here is, I have a radiation which is coming. I have kept the area here. This area, I am checking how much radiation is coming, energy of the radiation per unit area. What should I do? I will count total area divided total energy. I can count every energy everywhere, divide it by area. So that is energy per total, energy per unit area, and per second. I have to also divide by time. How long do I measure? If I measure it for 10 minutes, I have to divide it by time. Then I get magnitude of Poynting's vector. That is energy per unit area per second. I want energy in a given solid angle. Let us say this is a solid angle. This I have at making an angle. Let us say this. What is a solid angle? It's like a cone, three-dimensional cone. I want to see the energy radiation coming in this particular area. So then, if I know energy per unit area per second, if I want to know what is the energy in this solid angle, then I will say it is given by magnitude. This is energy per unit area per second. Multiply it with the area of the solid angle. Then I get energy emitted within that particular area. Or am I confusing you? What I am saying is defining what is meant by energy per unit area per second. I take energy everywhere, divide it by total area, divide it by total time. That quantity, what I write, is called as Poynting's vector. Okay, total energy that is available in the entire area, divide it by area into time. Anytime I do, that's what I get for Pointing vector. That means I have a physical identification. All right. But I do want to know in a solid angle, how much energy is coming. Energy per unit area is known, but I want energy in a given area. Why do I want a solid angle here? That is because whenever I keep measuring my radiation coming out of a nucleus, let us say, I have a detector, which is a finite region. So I want to check from a point source. I have, this is the region, all this is coming into the detector. So when I do experiments, I want to know how much of gamma rays are entering the detector. That is nothing but energy per solid angle, energy emitted into the solid angle of theta phi angle. That is, I have this region is some solid angle d omega. So I know what is d omega. D omega is known to you. Sin theta d phi is what is called as a solid angle. So I do have this solid angle, element of solid angle. I want to know how much of energy is coming into this region. So I have to write energy per unit area into time, area into time. That is what is my Poynting's vector. And then multiply it with which area that you have chosen, because you want it in that particular area. So I will say sin theta d phi. That is what I detect experimentally. So I have to say that. So I am explaining you what is the, why I am saying all these things. Energy per unit area per second is magnitude of S. But if I want to know what is the energy emitted into a solid angle element d omega, subtended by the detector. Detector is making an angle with the gamma ray, that is, which is entering. Whichever gamma rays enter into the solid angle are being detected. So this is what we get as modulus of S. Oh, I forgot R square d omega, because it is at a distance R. Let me go back. I forgot that. This is at a distance R into d omega is what I have. So energy, what is the area? Area is given by R squared d omega. This is the solid angle area. So I forgot about R squared. So I have to write S into R squared d omega, where R denotes distance from the source. I am far away from the source. R squared d omega denotes the area of the solid angle. So now I will say, consider a pure multipole radiation. Is there any confusion here? Do you understand what I said? I determine energy per unit area per unit time. That's what is Poynting's vector. Meaning of Poynting's vector is energy radiated per unit area per unit time. Fine. Now I want to know what is the energy emitted inside a solid angle at a distance r. So I have to write, suppose I ask you, what is the area of cross section? If I write a cone here, let us say this is the angle theta, and let us say this is r, this is r. This area, this whatever is this arc that I am writing, it is r into theta. If theta is small, I write it as the r into theta. A three-dimensional concept is, if I want to know what is the entire area covered by this, that is going to be r squared d omega. That's what we say. That is the area of cross section of whatever I have into the solid angle, of the solid angle. So your job is, if you know what is the area of cross section of the solid angle, then you know what to do, how to get energy emitted into the solid angle, which is subtended by the detector. Detector receives all the radiations which are coming into the solid angle. So I am saying S into r squared d omega is the distance. R squared d omega denotes the area. You check it yourself. Convince yourself that r squared d omega denotes the area subtended by the solid angle. Now I consider a pure multipole radiation. Let us, for example, take a electric type multipole radiation with multipole amplitude AELM that is coming into the solid angle element. That is, I am now going into further dissection of the radiation. What I am trying to tell you is some radiation is entering into the detector. Fine. Now I am making further classification. I tell you that radiation has its multiple components. Let me take a multipole radiation of the electric type with some given L value. For a given L value, you have coefficient AELM. This is entering into the solid angle, which means part of the radiation which is entering into the solid angle is a particular L type, M type, and electric type, and there is a fraction of which contains L, M, and E. That's what I'm saying. So this is entering. Then the energy is then given by magnitude AELM mod squared, and I'm writing some new quantity here, UELM theta phi d omega per second. What is meant by AELM mod squared, UELM theta phi d omega? This is nothing but, it's a little difficult to explain. So let me try to explain. So this is given by AELM mod squared and something that I am writing ZLM theta pi into d omega. How do I explain this? Okay, I will try. Okay. What is it that I want to do? My intention is to write energy per energy entered into the solid angle per unit time. This I told you, this is given by the magnitude of Poynting vector and r squared d omega. Is that fine? This is what I told you. And then I am simplifying this and writing it. When I simplify it, I have to write what is S. S magnitude of S is what? It is C divided by 4 pi B mod squared. And there is a r squared d omega. That is what I will get. And B is what? B mod squared is nothing but I have a L YLM of theta pi and e to the ikr divided by r magnitude whole squared. And at r is equal to capital R. I will take it at the distance is fixed to be r. What is the magnitude squared of this? That's what will give you my energy per unit area. So this is nothing but, this is e to the ikr, magnitude of e to the ikr. Can you tell me? What is this magnitude? I will ask you some simple things that you will already know. Then I will continue because I'm not doing something very, very complicated. You have to only connect with concept to concept. What is magnitude of a e to the ikr?
1.
1. So anything e to the I theta magnitude is 1. So you write a complex number as r e to the I theta, then magnitude of z is r. So that's what I am using. So if you write that, then what is B mod squared? Because Poynting's vector is given by B mod squared. So I will say your Poynting vector, yes, magnitude of yes is C divided by 4 pi B mod squared, but that is nothing but C divided by 4 pi. I have 1 over K squared, R squared was there. R is capital R because B is e to the ikr divided by kr into L acting on YLM. I am not able to write it. So that is what I have proportional to this kr. I'm not writing explicitly everything. So this is what I have. Then I want to take a magnitude square that is going to be divided by k squared r squared because r is fixed at capital R. I am fixing the distance at which I am measuring the radius. And then I have L acting on YLM of theta pi. Magnitude squared means dotted with vector, dotted with vector. This is what I should write. So I am writing all of it in a compact form now. So what I am saying is I'm using a different notation, but what I am doing is simply the magnitude of Poynting's vector. So that is going to give you AELM. That is with this probability it is coming. And I'm writing something as ZLM of theta pi into d omega. ZLM of theta pi is L into YLM star dotted with L into YLM. That is the magnitude square of LYLM vector. So now I don't want you to get worried about all this. How it comes, you should know it by looking into the expressions. This is called the angular distribution function, or what I'm saying is my emphasis here is for a given radiation in an angle theta pi, what is coming as energy, that is energy radiated, is going to be given by, it is proportional to something called as ZLM of theta pi d omega. And there is some factor here. This is what is called as angular distribution function. And if angular distribution function does not depend on theta phi, then radiation coming in this direction, radiation coming in this direction, all have same energy. But if it is not, then there is a particular angular distribution. That is what is the meaning that I am trying to emphasize. This is called ZLM of theta phi is called angular distribution function. AELM, UELM theta phi is then given by, that is AELM is the magnitude, how much of the radiation has L value given by 1, 2, 3, etc. And then multiply it with what is called as a angular distribution. If this is independent of theta phi, I get radiation coming in all directions are same. But ZLM of theta pi is given explicitly by half into LYLM star dotted with LYLM. So this is called the angular distribution function. I will just show you what is it explicitly. So I want to simplify this. You don't simplify it, but I write it so that you can calculate using this expression. I simplify what is LYLM acting on LYLM. So that is given by half into 1 minus M into M plus 1 divided by L into L plus 1, YL M plus 1 theta phi mod square. This is the expression that I am writing. Please remember this for now so that you have problems which you can simplify. Suppose I say a radiation has L is equal to 1, value is L is equal to 1 and M is equal to 0. We call this a dipole radiation with M is equal to 0. So if I check it, what is Z1 0 of theta phi? Angular distribution. In different directions, you have different energy of the radiation. That is, number of particles entering into different directions is different. How many particles are entering? It depends on theta phi. How do I get the expression for this? I have to calculate half and work out what is 1 minus M into M plus 1 divided by L into L plus 1. L is 1, M is 0. Substitute this, then you do get y11 of theta phi mod squared plus y1 minus 1 theta phi mod squared. So now, I had asked you to work out what is the spherical harmonic function for L is equal to 1, L is equal to 2, etc. There is a meaning for it because you need to use them when you want to check what is the angular distribution of gamma rays. So Z10 of theta phi depends on Y11 and Y1 minus 1. Y11 is given by this expression. Check it with your tables. Y1 minus 1 is given by minus 1 into Y11. I will write that. And we obtain simply Z10 of theta phi is 3 by 8 pi sine square theta. This is very important. If I ask a question, write an expression for angular distribution function. This you should remember. And given y11, y10, y1 minus 1, estimate what is the angular distribution function in the case of L is equal to 1, M is equal to 0. Or ask what is the angular distribution of a dipole radiation. Electric type, magnetic type, forget it. But what is the angular distribution function. This is the question. Then you have to be able to obtain Z10 theta phi is 3 by 8 pi into sine squared theta. So this is the angular distribution of energy for dipole radiation emitted per second into the solid angle. I'm writing it in English now. So this is the same. This is same for magnetic multipole radiation also. I will have to write AM LM instead of a AE LM. So I get the same ZLM function, or I do know that angular distribution of energy emitted is the same for both electric and magnetic type multipole radiation of same multipolarity. What I am talking in terms of what is called as what is physics of it. So what I am saying is, I told you, I promised you that you have a radiation coming out. Can you determine its multipole value using your experiment? That's the agenda for us. I have a radiation. You have a detector here. Can you determine what is the L value, what is the M value, whether it is electric type or magnetic type? So that is what is the idea. If I have introduced it theoretically, is it possible for you to determine it experimentally? That is the idea. In order to do that, now I have shown you that energy emitted, energy means number of counts of the gamma rays basically, with some energy into the solid angle d omega, r squared d omega. That is the area of the solid angle. So this is going to be proportional to, if it is a electric type radiation, I get this mod squared into some function z lm of theta phi. This depends on the angle and d omega. So that is d omega is there. So this is what is the energy radiated, and you can, what is left hand side is measured experiment. That is experimental, but right hand side is a function of theta phi. So you will say a radiation coming here with a given L value here, and radiation coming here with the same L value, they have a different distribution. Distribution depends on ZLM of theta phi. Now suppose I plot what is ZLM of theta phi as a function of, let us say, theta, when L is equal to 1, M is equal to 0. You know that ZLM of theta phi, when L is equal to 1, M is equal to 0, energy ZLM of theta phi is proportional to sine squared theta. You have seen it, how I worked it out. So I have energy given by sine squared theta. If you plot sine squared theta, how does it look like? So sine squared theta as a function of theta. You know that sine squared theta is maximum at theta is equal to when? When is it maximum? Sine squared theta versus theta. When is the function maximum? I want to check if you are sleeping or if you are listening. Sine squared theta. Do you know the value of sine squared theta for different theta values? And can you tell me when is it maximum? I will
90 degrees.
90 degrees. So I will say it is 90 degrees. Then sine squared theta is maximum. Otherwise, it is something like this. So if I keep a gamma ray, which is coming, making an angle, let us say, this is theta value. When theta is equal to 90 degrees, maximum number of radiation is coming in that direction. There is a number of counts. Energy radiated is large when theta is equal to 90. Energy in other directions is smaller. That tells you that it's a dipole radiation. A dipole radiation means L is equal to 1. It has a typical angular distribution. That is the agenda for us. So we have determined that angular distribution of a L value, given L value, M value, is typically given by this kind of a distribution. Okay, but I can only determine what is the distribution tells me what kind of a L, that is it a dipole, Is it a quadrupole? Is it some higher rank L value? By determining the distribution, angular distribution tells me. If I count the gamma rays coming at different angles, that tells me whether the radiation is a particular angular, that is L value of the radiation can be determined. But I am unable to determine whether it is electric type or magnetic type, because both electric type and magnetic type angular distributions are going to be same. That's the result that I get after all this exercise, which went for around 1 hour now. So in order to determine what is the parity of the radiation, or whether it is an electric type or magnetic type, we need to do further measurements, which I will not tell you, but it is mentioned here. To determine parity of the radiation, one has to also measure polarization of the radiation. You know that electric and magnetic fields are polarized, right? Do you know that? There is a polarization component of every electromagnetic radiation has its own polarization. That is it elliptically polarized? Is it horizontally polarized, etc.? When I say energy, any polarization is counted. If it is horizontally polarized, vertically polarized, I don't care. I check what is the total energy, irrespective of whether it is polarized vertically, horizontally, everything. I count it. But if I want to check for a given polarization, what is the energy? That is going to tell you whether it is electric type or magnetic type. And have I proved it? No, I haven't proved it. I'm only telling you the known result. So if I know what is the energy at different angles, it will tell you the multipole type. What is the L value? L is equal to 1, 2, 3. If you plot the angular distribution, you know whether it is going to be L value, dipole or quadrupole or whatever. But if you also check what is the polarization of the radiation emitted in a particular direction, that will be able to tell you whether it is electric type or magnetic type. And I'm not discussing that. It's a little involved. So I'm telling you it's possible to determine electric type or magnetic type if the radiation has a multipole value and all. So I will stop it at this because it is still little more dense. What you know now at this point is, if you are checking what is the radiation emitted and getting into a detector, you are determining what is the multipole value can be determined if you look at it at different angles. I derived what is the Poynting vector, and the Poynting vector contains an electric and magnetic field, and in the wave zone, which is of our interest, that is we are far away from the source, in that region, I know what is the magnetic field associated with the radiation. So I can simplify what is the energy radiated into a solid atom. I just showed you, indicated to you what is that calculation. Once you do that, you know that for a typical L value, there is a particular angular distribution, and that particular angular distribution is going to discriminate what type of a radiation it is. Is it L is equal to 1 or dipole radiation? Is it L is equal to 2 or quadrupole radiation? If you give me experimental angular distribution of radiation, I will be able to tell you whether it is multipole type, L is equal to 1, L is equal to 2, etc. But this still doesn't determine what is the type of radiation, electric type or magnetic type, which I introduced day number 1 in the gamma decay class. So in order to determine whether it is electric type or magnetic type, we need to have what is polarization of the radiation. That is every electric vector, magnetic vector. When you do your first semester M.Sc experiments, you are doing some experiments with polarization of electric field, magnetic field, and work out whether the radiation coming, whether the light coming, is it elliptically polarized or not, etc. Polarization is another concept for electromagnetic fields. So I want to determine. I'm not telling you more about polarization, but I'm only telling you that polarization of the electric and magnetic fields is important factor. It is important feature, theoretical feature, which reflects whether the radiation is of electric type or magnetic type. With that, I just stop it now. And if you have any questions, You may ask me for 2 or 3 minutes. I will keep it open. Any questions? Or you may go, leave the